Today we are going to study about metal nanoparticles. Before starting with metal nanoparticles, let us discuss what semiconductor nanoparticles are and how do they behave and which kind of photons do they absorb and emit. So if the size of a nanomaterial, a semiconductor nanomaterial, is of the order of its de Broglie wavelength of the charge carrier, then it will show quantum confinement effects. But if the size of the material is very larger, greater than the de Broglie wavelength, it will not show any quantum confinement effect. In smaller nanoparticles, because of the quantum confinement effect, the energy band structure will become discrete and the energy band gap will increase as the size will be smaller and smaller. Because of it, the absorption energy of the particle will also change. So as the particle will become smaller, it will absorb higher energy photons. It means lower wavelength photons. So if we draw absorption graph for this material, we see that smaller nanoparticles absorb at lower wavelengths and larger nanoparticles absorb at higher wavelengths, which corresponds to a lower band gap, and a lower wavelength corresponds to a higher band gap. But in metal nanoparticles, there is also a shift in the absorption spectra, but the reason for this shift is not quantum confinement effect but plasma oscillations. So in bulk metal nanoparticles, there will be no size dependence, but as the size of the material ranges in nanometer range, it will show size dependence. The absorption spectra will show size dependence. While if the size becomes of the order of the de Broglie wavelength, then quantum confinement effect will take place and the energy band structure will become discrete and it will be size dependent also, but the reason will be quantum confinement effect. While at a larger wavelength, when the size of the material is of the order of its mean free path, then it is size dependent, but the reason for this size dependence is plasma oscillations or size dependence of plasma oscillations. So now first of all let's discuss what are plasma oscillations. So first of all, what is a plasma? So if we have ions, molecules and electrons, atoms, a mixture of all of these is called plasma. But in a metal you have a sea of electrons and an arrangement of ions. So this sea of electrons actually will oscillate with the electric field. If we apply an electric field with it together, and all of these electrons will oscillate together with the electric field, and it will act as an electron plasma. So we are considering this sea of electron as an electron plasma, which only consists of electrons. So if a photon is incident on this, it means, as we've discussed in the last page, that if a photon is incident on these particles, which are of the order of nanometer range, then some of the wavelengths of the photons, they are absorbed. You have these absorption peaks. So if larger nanoparticle, it absorbs at larger wavelengths, smaller energies, and smaller nanoparticle absorbs at smaller wavelengths, larger energies. So why does the photon is getting absorbed by a metal? And this is what we are going to discuss. So we see that when a photon is incident on a metal, it is getting absorbed. But what is a photon? Photon is an oscillating electric field. While we have studied that metals are reflective to electric field and the electric field inside a metal is zero. So we know that the electric field inside a metal is zero. It doesn't penetrate the metal. So this happens when this electric field is static. Well, if the electric field is oscillating, then there are some different conditions that will take place. So electric field will not penetrate the metal if it is static or it is oscillating at a lower frequency from DC to gigahertz frequency. While at a higher frequency, the metal will show some electron oscillations or plasmon oscillations. And this is what we are going to discuss. So, but because now what we require is that how photons will enter a material. So, we will have to discuss about permittivity, because that will give you an idea of how much electric field a particular material has the ability, that how much electric field will pass through it. So, we know that any material has some natural frequency. Similarly, the electron cloud in a metal has also some natural frequency. If the frequency of the photon matches the natural frequency of the metal, then the electrons will oscillate with a larger amplitude and will give rise to a very large amount of electric field. So, electron cloud moves with very large amplitudes, creating large electric field. And this condition, where the frequency of the photon matches the frequency of natural frequency of the electrons, is known as the resonant conditions. And these oscillations are known as plasma oscillations of the electrons. Oscillation of the electrons are known as plasma oscillations or plasmon oscillations. So, the resonant oscillation of conduction electrons is called plasmon resonance. Now, in a nanomaterial, because the size of the material is very small and it has around 10 to the power 3 to 10 to the power 4 free electrons, and all of them are oscillating together. So, it means, and when a particular photon is incident on this material, which has a frequency or the wavelength of the order of the natural frequency of the order of the natural frequency of the electrons, then plasma oscillations will take place and a large amount of electric field is generated. And this generated electric field, because it is concentrated in a very small area, very small volume, it is a very concentrated electric field, and it is around 100 to 1000 times stronger as compared to the incident electric field. And such kind of resonance is called localized plasmon resonance, because here the electric field gets localized. And so we have plasma oscillations in bulk as well as in nanomaterials. So the quanta of plasma oscillation is called plasmons. It is similar when in electromagnetic radiation, a quanta of electromagnetic radiation is called a photon. Similarly, a quanta of plasma oscillations is called plasmons.